All right, this is section 11.6. In this section, we're going to cover a few topics: events involving the word not, or, and also working with odds. All right, so let's take a look at our first set of rules here. Complement rules of probability. It says the probability that an event E will not occur is equal to 1 minus the probability that it will occur. All right, and the same thing for the second option. It's just that it's saying that the probability of the event is equal to 1 minus the probability of the event not occurring. So all of these are saying the same thing. They're just solved for different items, whether it's not the event or the event. Another way you can even look at this is to say the probability of the event plus the probability of not the event is equal to 1. And they also have set notation on here that they're using with the not E. All right, so if you want to look at this more on a visual basis, you can think of your Venn diagrams. We can say, here's my set A, and this is my universal set. So if I have set A inside the circle, everything outside of the circle that's still contained in the universal set is A naught. All right, let's look at our first word problem. If you are dealt one card from a standard 52 card deck, find the probability that you are not dealt a queen. All right, so you remember we're getting dealt only one card and we're in a 52 card deck, a standard deck. And we want the probability of not dealt a queen. All right, so we have a few ways that we can look at this. So we have 52 cards. There are 4 queens in a deck of cards, so we're going to minus the 4 queens. And that leaves us with 48 that are not 48 cards that are not queens. So if we had to look at the probability, remember the probability is going to be a fraction. Unless it's 0 or 1, it will be a fraction. And we're going to take a look at the fact that we have 48 cards that are not queens out of the 52 cards of the deck. And when we use this, we get 12 over 13. And this is the probability of not being dealt a queen. All right, there's another way to look at it, and that is to use those formulas on the previous page that we had. So we have the probability again of not dealt a queen. According to the front part where it says the probability of not the event, on there we will have 1 minus the probability of being dealt a queen. All right, and then we know that we have 4 queens out of 52 cards. And again, if you place this into your calculator, you will get 12 over 13. So once again, we're coming up with the same answer. It's just a different way to work this problem. So what you want to do is look at both of these options and see which one makes more sense to you. Some folks have an affinity to go ahead and just subtract the 4 queens and find out how many cards are not queens and work with the first option. It is your choice. All right, let's talk about mutually exclusive events. It says, if it is impossible for events A and B to occur simultaneously, the events are said to be mutually exclusive. Events A and B, impossible to occur simultaneously. So if, again, you're looking at a Venn diagram, you are looking at, here is my event A, here is my event B, contained in my universal set, of course, and there's no overlapping, right? A and B cannot occur at the same time because they're not touching or crossing. So therefore, they are considered mutually exclusive. All right. When we have mutually exclusive events, you have to look for this word or right here. It says or probabilities with mutually exclusive events. So let's look. If A and B are mutually exclusive events, if they are exclusive, such as that Venn diagram, then you're going to just take the probability of A plus the probability of B, and you will have your answer. All right. Using the word or, remember, or back in set notation is the same thing as union. So if we're taking the union of both sets, we're still going to take the probability of A plus the probability of B. All right, if one card is randomly selected from a deck of cards, what is the probability of selecting a king or a queen? So let's define what we're looking for. We're going to look for the probability of selecting a king or a queen. When you see that word or, we need to ask, is this mutually exclusive? All right, so what you're asking yourself is, can you select one card? Can that one card be a king and a queen at the same time? Well, no, because we have kings here and we have all our queens over here, and these are considered mutually exclusive. You can't be both at the same time. All right, so now that it's both mutually exclusive, that means to find the probability, we're going to take the probability of a king plus the probability of getting a queen. And we're just going to add those together. So we know the probability of a king is that we have 4 kings out of 52 in that deck of cards. And the same thing with the queens. We have 4 queens out of 52 cards. And if we add those together and reduce, we should come up with 2 over 13. Remember, once again, your probability is a number that falls between 0 and 1. It can be 1 and 0, but anything in between. All right, so this time we still have the word or that we're looking at, but it says or probabilities with events that are not mutually exclusive. All right, so events, if you want to know what that looks like, we would have event A here, and this would be event B, and there's my Venn diagram. And if you notice, they have a little overlap in the middle here. All right, and this middle part where it's overlapping, this is A and B. Remember, B and is for the word intersection. Set notation looks like that. All right, so let's take a look at our formula. It says if A and B are not mutually exclusive events, then in order to find the probability of A or B, we need to take the probability of A plus the probability of B minus the probability of A and B, the intersection. And that same thing with the set notation. In a group of 25 baboons, 18 enjoy grooming their neighbors, 16 enjoy screeching wildly, while 10 enjoy grooming their neighbors and screeching wildly. If one baboon is selected at random from the group, find the probability that it enjoys grooming the neighbors or screeching wildly. Wow, what a word problem. So what I'm going to do first of all is I'm going to use some letters here. For grooming, I'm just going to say that is G. And for screeching, I'm going to say that's my set S. All right. So we're looking for the probability that it enjoys grooming. or screeching. All right, when we see that word or, we have to ask ourselves, is it mutually exclusive? So in this case, since they told us that there are 10 that enjoy grooming their neighbors and screeching wildly, this and part, that means that there's some overlap in the two sets. So we have grooming here, we have screeching right here, and this part in between is grooming and screeching. All right, so we do have a little bit of an overlap right there. So according to this, these are not mutually exclusive. And for the not mutually exclusive, you're going to have the probability of grooming plus the probability of screeching minus the probability of grooming and screeching. All right, so the probability of grooming, if we take a look at that, it says that we have 18 that enjoy grooming. So 18 out of a total 25 baboons. There's your probability for grooming. Then we have the probability of screeching, and it says that 16 enjoy screeching. So plus 16 over 25. 16 over 25 represents the probability of those that enjoy screeching. All right, minus, and it says the probability of grooming and screeching. So we have 10 that satisfies that condition. 10 out of the 25 enjoy grooming and screeching. And if you place this in your calculator, you will find you have 24 divided by 25. And this will be your probability of these not mutually exclusive events. And if we take a look at our Venn diagram here, if I wanted to fill this out, remember how we would always fill out the innermost portion first? So we would start where the intersection is, right in the middle. And it says for both that enjoy grooming and screeching, we know we have 10. All right. If we want to look at those that enjoy grooming, and I'll put a little blue dash here. So just for grooming purposes, that has a total of 18 that enjoy grooming. So since I have 10 in the middle, that means I have 8 over here. 8 plus 10 is a total of 18 that enjoy grooming. All right, and then for the screeching here, I'm going to put this little green line that goes around the circle. The screeching has a total of 16. That innermost portion is 10, and 10 plus 6 will give me the 16. All right, so if you take a look at this right here, remember this is all inside your universal set. If you take the 8 plus the 10 plus the 6, you will get 24, which is that numerator. Remember there's 25 baboons, so that means one baboon out here does not like to do the grooming or the screeching. All right, but this is your numerator. And you just divide by 25 and you'll have your probability. For this problem, we're going to be looking at the spinner in the lower right-hand corner. And it says, for this spinner, it is equally likely probable that the pointer will land on any one of the 8 regions. So we have 8 regions numbered 1 through 8. If the pointer lands on a borderline, spin it again. All right, find the probability that the pointer will stop on an even number or on a number that is greater than 5. So what I'm going to do first is just make sure I have my sample numbers, and I know that I have 1 through 8 available to us. All right, then we're talking about the probability of even numbers. So if I want to look for even numbers, my even numbers in that set is going to be 2, 4, 6, and 8. And then a number greater than 5. So I'll say number here greater than 5. So the numbers that are greater than 5 would be 6, 7, and 8. All right, just defining what my sets would look like. Okay, so what we're looking for is the probability that the pointer will stop on an even number or a number greater than 5. We have the word or, and we have to ask ourselves, are these events mutually exclusive? Making sure that there is no overlap of those two of being even and greater than 5. Well, if you take a look over our sets that define even and numbers greater than 5, they overlap because they both have a 6 and they both have an 8. So therefore, these are not mutually exclusive. We're going to follow the formula for not mutually exclusive. So we're going to take the probability of an even number plus the probability of a number greater than 5 minus the probability of the even number and a number greater than 5. All right, so first the probability of an even number. When we look at our even numbers, we have how many values there? Well, we have 1, 2, 3, 4 numbers are even. So that's going to be 4 out of the total 8 numbers. And there's our plus sign. For numbers greater than 5, let's go count those. We have 1, 2, 3 numbers that are greater than 5, so 3 out of 8. And then we put our subtraction sign. Numbers that are even and greater than 5, well, there are 2 numbers. There's the number 6 and the number 8. So that's 2 items, 2 out of 8. Right, and then you place this in your calculator, and you will find the probability of having an even number or a number greater than 5 is going to be 5/8. This next slide shows probability to odds. It says if P of E, the probability of E, is the probability of event E occurring, then the odds in favor of are found by taking the probability of E, which I'm just going to reiterate this formula, probability of E will occur divided by the probability that E will not occur, or in this case, not E. For the odds against the event occurring, you're going to take the probability of not E, probability of the event not occurring, divided by the probability of the event occurring. So if you take a close look at both of these ratios, you can see that they are reciprocals of one another. So if we go in and we find the odds in favor of the event and we get our answer as a fraction, all we have to do is to reverse the fraction, take the reciprocal of it, and you will have found the odds against E. For this exercise, it states that you roll a single 6-sided die. Part A says find the odds in favor of rolling a 2. All right, so let's first take a look at our 6-sided die. My sample space for a 6-sided die is that we can roll a 1, 2, 3, 4, 5, or a 6. And we're trying to find the odds in favor of rolling a 2. So we're looking at the odds in favor of rolling a 2. So in this case, the odds in favor would be the probability of the event rolling a 2 divided by the probability of not 2. This is directly from the formula on the previous slide. All right, so then we have to fill in what is the probability of 2? When we take a look at our sample space, well, there's only one item that's a number 2. So that means we have 1 out of 6 sides. That is the probability of a 2 occurring. And then it will be divided by, and then we're going to go find the probability of not 2. So for the not 2, we have to count out numbers that are not 2, and we have 1, 2, 3, 4, 5 of those numbers are not 2. That'll be 5 over 6 for our denominator. When we take 1/6 divided by 5/6, we are going to get 1 over 5. All right, so that is your ratio. And it can be expressed as 1 to 5. All right, the odds in favor of rolling a 2 is 1 to 5. And that was part A. Then we take a look at part B. Part B says odds against rolling a 2. So we just learned that for the odds against, all we have to do is reverse our answer from the previous part A. And I'll go ahead and write this down. Odds against, we do the probability of not rolling a 2 over the probability of rolling a 2. All right, so we had 5 over 6 divided by 1 over 6. And this will give you 5 over 1. Now you remember you want to keep this as a ratio or as a fraction so that you can rewrite this properly to 5 to 1. You want to rewrite it as 5 to 1. If you put it in your calculator and you just get the answer 5, you might not be sure how to write your final answer. All right, so the odds against is 5 to 1. Odds in favor, 1 to 5. For the last 2 slides, we just covered probability to odds. We used probability in order for us to calculate the odds in favor of and the odds against. All right, so this time we're going in reverse order. We're going to start with odds, and we will convert it to a probability. In order to do so, we need to utilize the odds in favor of the event, the result of that, so that we can get A to B, label our A and our B, so that we can use this formula. The formula says the probability of that event is A over A plus B. All right, so let's go back and visit that previous problem that we had, the odds in favor of rolling a 2. Right, the odds in favor of rolling a 2, we came out with the result of 1 to 5. That was our answer. According to this formula, now that we have these odds, 1 to 5, we can label the first number as A, the second number as B, and from here we can figure out the probability. So the probability of rolling a 2, which we already know what this is because we found out on the last slide. Probability of rolling a 2 is to take A, which is 1, over A plus B, 1 plus 5. That'll give us a true result. It does take 1/6 probability to roll a 2. For this final slide, it states the odds in favor of a particular horse winning a race are 2 to 5. What is the probability that this horse will win the race? All right, so for us to find the probability of this horse winning the race, we need to be working with odds in favor of. So we can see in our reading that it did supply us with odds in favor of, and the odds are 2 to 5. So we do have what we need in order to find the probability. So let me write this out. The probability of the horse wins the race is what we're looking for. So let's define our A and our B from the odds. Now, according to that formula, it says the first number would be our A, which is the number 2, and our second number 5 will be our B. Using the formula to find the probability, we'll have A, which is 2, divided by A plus B, or 2 plus 5. And doing some basic math, this will result with 2 over 7. So the probability that the horse will win the race is 2/7. This will conclude the lecture.